So hi everyone, and welcome to today's class. This is our second topic, statistical inference. We have already looked at the probability distributions, the binomial, the Poisson, and the normal distribution. So let's now start what we're calling the statistical inference or inferential statistics. And before we proceed, I would like us to remind ourselves something that we learned in, that should be Business Statistics 1, that statistics as a discipline is broadly classified into two. So we have what we call theoretical or mathematical statistics. And basically what happens here is among other things, the derivation, the development, the proof of theorems, rules, formula, etc. that are used in statistics. So these are the guys who develop the formulas that you know, or the rules, or the axioms that you know are used in statistics. So that's developed by the mathematical or theoretical statisticians. Then on the other hand, we have the applied statisticians, applied statistics. And basically what these guys do here, they, sorry, let me say this. So it entails, so this branch of statistics entails the use or the application of the rules, formulae, the theorems, etc. to solve real world problems. So you use the formulae or the rules or the theorems that were developed by the mathematical statisticians to solve real world problems. That explains why you guys are in this class, because some of you are coming from finance. There are problems in finance that need to be solved using statistical methods. Some of you are in human resource management. There are problems in human resource management that needs to be solved using statistical methods, and many other areas like marketing, accounting, even entrepreneurship, and so on and so forth. Okay. Then applied statistics can be further classified into two. We have on one side we have the descriptive statistics. And basically, this involves the use of sample information or sample data. So in this branch of statistics, we use sample data to obtain two things. To obtain both numerical and graphical or tabular summary values. To obtain numerical or graphical or tabular summary values. So key here is that we use sample information. I guess you know that a sample is a representative subset of the population, where the population is a complete set of all the elements of interest in a given statistical inquiry. Okay, so here this is presented in several ways. So graphically, when we talk about graphically, we talk about the graphical presentation of data. You can use pie charts, you can use bar charts, you can use histograms, ogive curves, and so on and so forth. You can also use tables. Okay, and the most widely used type of tables are what we call the frequency distribution tables. The frequency distribution tables. I think we mentioned this when we recalled this when we were introducing the concept of probability distributions. In addition to frequency distribution tables, we also have contingency tables. When we talk about the frequency distribution tables, mainly this is used for numeric data. When your data is numerical, either discrete or continuous, you present it using frequency distribution tables. But if your data is non-numeric, this is technically known as qualitative. Things like gender and what? Let's say you can talk about gender here. You can have male and female. And then you can talk about the smoking status, either smoker or not smoker or non-smoker. So that way, this is a simple table. It's called a two-way table, where we have only two variables, where the first variable is the gender of the person, and the other one is the smoking status. Smoking status. So smoking status here is a qualitative variable, just like gender here. So what you end up with here are the counts. So here you have counts. So maybe the counts, you can call them the number here, N11, N12, N21, and N22. So that's a contingency table. So this forms part of descriptive statistics, okay? Then the second part is numerical summaries. Numerical summary values coming from the samples. So these numerical summaries are called statistics. If it's one, it's called a statistic. Statistics, huh? So this is where you find things like measures of central tendency. Measures of central tendency. Things like the mean, the median, the mode, and so on and so forth. Then we have measures of skew, measures of dispersion. Measures of dispersion, the most important of them being the standard deviation. There are others like the quartile deviation, the range, and so on and so forth. Then we also have measures of skewness and kurtosis, among other things, including things like regression and correlation. So if you use sample data to perform any of these etc, so this is part of what we are calling the numerical summary values. These are numerical summary values. Okay. Now, on the other hand, here we have this. This is descriptive. So we have here what we call inferential statistics. Okay, that's our topic. That's our topic today: statistical inference. So we are looking at this branch. We are looking at a branch of applied statistics, and we'll notice that the items that I've listed under descriptive statistics, that is the formulation of frequency distribution tables, the contingency tables, calculation of the mean, the median, the mode, measures of dispersion, skewness, and so on. All those were captured in, or all those were done in business statistics 1, except now regression, which we have moved to regression analysis and correlation. This one has been moved to this unit. So we'll be covering this bit here. We'll be covering that bit here. Then the inference that revolves around regression and correlation will be done in the next unit for the guys who are doing finance in econometrics. That's when we'll look at the inference for regression coefficients. So we have already covered this. So we'll be performing inferences around most of this, around things like this. But I think the scope in this course will be just a few of them. We will not be performing inference on all of them. Okay. So when we talk about inferential statistics, this entails making predictions about population parameters based on sample information or based on sample statistics. So it's like inferential statistics is dependent on the descriptive statistics. So after we obtain these guys from here, after we obtain, for instance, the sample mean here, we have the sample mean. After we obtain the sample mean, we may want to make a prediction or an estimation about the population mean. We make an estimation or a prediction about the population mean. The population mean is what is an example of what you are calling parameters. I'll be explaining these terms when you get started. The population parameters. So you use the sample information to make predictions about the populations. And we make predictions about populations because, number one, we assume that populations are always infinite. So if populations are infinite, that's why we are not able, or it's not convenient for us to obtain things like the mean from the population or the standard deviation and so on and so forth. So we only have hypothetical values. These are guessed values, maybe from experience, that will help us to guess about the population parameters. But usually what we have at hand is the information from samples. So that is the information we want to use to make predictions about populations. So basically that's how you classify statistics. And this was just to show you that we have actually covered part of, we have covered quite a lot under the descriptive statistics. So now I want to conclude the other bit of inferential statistics, of applied statistics, by looking at now, how do we make the predictions? How do we make conclusions about populations based on the information we got from sample or from descriptive statistics? So let's start by defining the concept of inferential statistics. Definition. So definition. Say that statistical inference is the process of making predictions or estimations about population parameters which are always unknown. Population parameters are always unknown. That's why we are estimating them using sample statistics. Or using summary values obtained from or calculated from samples. Okay. So this process here entails two main things. So this process entails, or we can say that this statistical inference can be broadly classified into two. So there are two main sub-branches of statistical inference. Number one, we have estimation. And number two, we have hypothesis testing. Those are the two main things that happen under statistical inference. Okay, so maybe if I were to have a sub branch here, I'll be talking about estimation, and then here I have hypothesis testing. Okay, and hypothesis testing. Those are the main things or the main processes there. Okay. So when we talk about estimation, this comes in two ways. So we have what we call point estimation. This is when you use a single value from the sample to estimate the unknown population value. For instance, if you get X bar, if you get the mean from the sample is 20, you can use this one to estimate mu. So you can say mu is approximately 20. So this is the sample information. These are sample point, then or these are point from the sample, and then this is the population. So if you get the mean is 20 from your sample, then you may want to claim that the mean of the entire population is not different from 20. So that's a point estimate. It's not a very popular way of estimating, because we know that if you pick a sample, the sample must be random. And if you're picking a subset of the population, then you should know that it is not the only possible sample that you could have been selected there. So possibly if you chose another value, another sample, you find that the value of X bar will be slightly different or quite different. So you find that every possible sample might be having a different value of an estimate. So point estimation is not very reliable. So to take care of that limitation, we have what we call the interval estimation. Interval estimation. So instead of using a single point like this, you create an interval like this. You say between 15 and 23. So you say that you are maybe this percentage confident that the true mean of the population is between 15 and 23. So you use an interval, which is much more accurate, And you find that even if you are to take different samples, you will find that most of them will have their value of mean falling in between that interval. Okay. So that's the estimation. Our focus in this class will be interval estimation. And this will come in the form of what we call confidence intervals. So we'll be computing confidence intervals for the mean and also for the proportion when you are sampling from one population or when you are sampling from two populations. Okay. Then on the other hand, we have hypothesis testing. So we'll put a lot of effort, a lot of emphasis on hypothesis testing, where an hypothesis is just a claim about the population, okay? It's just a claim that you make or the researcher makes about the population. Then after you make that claim, you collect information from the sample. That information obtained from the sample will either support that claim or fail to support that claim. So we'll be rejecting or failing to reject, we can say accepting the claims or the hypotheses that we shall be making about the population. For instance, I can make a claim that, this is just an example, that the mean age of students in this class, let's say is 24. I can make such a claim. But usually the claim is not, we usually don't make wild guesses. You need to have some past information about the students who usually join this particular class, okay? If they are government-sponsored students, they are full-time students. If they are part-time students, if they are weekend students and DL students, I need to have a lot of information from past records. Then using that past information, I can make a claim about the mean of the entire class or weekend class. Then using sample information. So after I make this claim, this is my claim, then I need to go and choose a sample. From the said population. Then I'll get a value of X bar. So usually this is now your mu naught. It is a claimed population mean. Then I'll collect a sample. I'll choose a sample, a random sample. Then I find the mean. Maybe I'll get the mean is 20. So the process of hypothesis testing will be to check whether this value actually supports that claim. So we'll be going to the details a little bit later, okay? So, but basically those are the processes that we shall be dealing with: interval estimation and hypothesis testing for one sample and two independent samples, okay? So let's define some other terms, a parameter. Let's define this term, parameter, and we say that this is a numerical summary value obtained or relating to the population. In most of the cases, it is not calculated. It is just a claim. It's just a belief, okay? A numerical summary value that is relating to the population, okay? So things like population mean, okay? Population standard deviation, etc. Okay. Then the other related term is what we call statistic. We say that this is a numerical summary value, calculated. In this case, it should be calculated from the sample. Things like sample mean, and sample standard deviation, etc. Okay. So let's look at the assumptions under statistical inference. There are two main assumptions. Number one is that the sample analyzed is large. Sample analyzed is large. That is, if n is the size of the sample, then n is bigger than 30. That's what we call a large sample. If the number of observations, so that is, if the number of observations, sampled, or the number of individuals, I think should be individuals, or elements sampled is more than 30. So that's what we call a large sample. So we shall be assuming a large sample all the time. You will see the reason a little bit later. Number two, the second assumption is that the sample is random. It's randomly chosen, sorry. The sample is randomly chosen. You say that a sample is said to be random. A sample is said to be random if every other possible sample in the population under consideration, in the population has an equal chance, or probability of being chosen. If every other possible sample in that population under consideration has equal chance of being selected. Or you can say a sample is said to be random. A sample is said to be random if the elements are chosen in such a way that every element in the population has equal chance of being selected, or sampled. So those two versions of definition are equivalent. So here in the second one, talk about every element in the population has equal probability of being chosen. So that means there's no bias. To a layman's language, in a layman's language, means that there's no bias. So if you are the one choosing, then your personal biases are eliminated in the process. So there are various ways of choosing such samples. You can use the lottery method if the number of elements in the population is quite small, or you can use a computer-generated random numbers to obtain the elements in a random fashion. Okay. So let's look at some important denotations, some important symbols that we shall be using in statistical inference. And we say that usually parameters are represented using Greek letters. In most of the cases. Of course, there are exemptions. And while sample statistics are represented using Roman letters. Most of the cases, lowercase letters. This one should be Roman letters. Represented using Roman letters. Okay. So examples. I'm just going to show you a few of the symbols that we shall be using here. So let's create a table with 5 columns. So we have the first column here is the size. Then we have the mean. So those are the summary values that we're talking about. We have the standard deviation. We have the proportion like that. So we have that table. Then here we have population. Here we have the sample. So the population, so this cell here represents the population size here. So the population size is denoted using a Roman letter, not a Greek letter. Roman letter, capital N. There's a reason why we don't use the Greek letter corresponding to that. Then the population mean is denoted using the Greek letter mu. The population standard deviation is denoted using the Greek letter sigma. And of course, the variance is sigma squared. And the population proportion denoted using pi. Then sample size denoted using small letter n. So for the population and sample size, we use letter n, Roman letters, but we use lowercase for the sample and uppercase for the population size. Then the sample mean is denoted using x bar, assuming the variable of interest or the measurements are denoted by x. So if the measurements were denoted by y, it would be y bar and so on and so forth. The sample standard deviation denoted by small letter s. And the sample proportion will be denoted by the small letter p. Small letter p. So these are some of the symbols that we shall be using in the context of statistical inference. Any question there? So now let's move on to the sampling distribution. And we are going to illustrate the concept of sampling distribution using the mean. So we shall be talking about the sampling distribution of the mean, but you can also argue the sampling distribution of other things, like the sampling distribution of the proportion, the sampling distribution of the regression coefficients, and so on and so forth. Okay. So in the notes, I've given you some example. I'll just read out, but I illustrate the concept of sampling distribution using a simpler example. You are told, suppose you own a factory which manufactures fluorescent light tubes. Okay, you can think of a company like Philips that manufactures fluorescent light tubes. Then it will be useful both for advertising and for monitoring the efficiency of your plant to know the average length of life of those tubes. Okay, so if you want to come up with an advert, you may want to mention the length of life, the mean length of life of your tubes. Okay, then clearly, because we expect that such a company would be producing maybe millions, hundreds of millions, or maybe billions of tubes, knowing that this is an international company. So clearly, it is not possible for the management to test every single tube that is produced by the company. It is not possible for them to do that. So what they do through the quality control office, they pick a sample. They pick a random sample. The sample must be random. They pick a random sample of size n. So they pick a random sample of size n. And then they measure x, where x is, this is x hours, the length of life of each tube in the sample. So you measure x, the length of life of each tube. Then after that, then calculate x bar and s. You calculate x bar and s, where x bar is the sample mean and s is the sample standard deviation. So these two values here will be the estimates. This will be the estimates of the population parameters will be the point estimates of the population parameters mu and sigma. Okay. Then we say that this is, of course, you will make your conclusions based on one sample. But remember, there are so many other samples that could have been considered. So we want to explore. Suppose we calculate X bar from all the different possible samples. And for convenience, I want to give another illustration. Consider a population of size n is equal to 3 with the elements. So these are the members of that population, A, B, and C. Okay. And the corresponding measurements of A, B, and C are 1, 2, and 3. For convenience, I'm choosing those are the measurements. Maybe those are the first. Maybe the first tube is 1 hour. Maybe the second one is 2 hours. Maybe they are years. Maybe 1 year, 2 years, and the other one is 3 years. That's the population information. Then suppose for some reasons you want to choose a sample of size n is equal to 2 from this population. Okay, then calculate X bar and S from that sample. So of course, if you deal with only one sample, you'll end up with a single value for each one of them. But let's explore how many different samples can we choose from here? And to make the example more interesting, so let's suppose you sample with replacement. Then how many different samples can be chosen? And what are the corresponding statistics? So we have a population here containing 3 elements, which is very, very small, of course, very unrealistic. We're doing this for the sake of illustration. Then we want to choose 2 elements from this population, and we are deliberately sampling with replacement. So once you pick a tube, assuming these are fluorescent tubes, once you pick, you measure, you can return it to the population, then you mix again, then you choose again, like that. Okay, so let's list all the possible samples. So let's create a table here where the first column is possible samples. So it is possible for you to obtain a 1, and then when you return, you choose a 1 again. It's possible for you to pick A twice when you are sampling with replacement. Then you can choose 1 under 2, 1 under 3. You can choose 2 under 1. You can choose 2 under 2. You can choose 2 under 3. You can choose 3 under 1. You can choose 3 under 2. You can choose 3 under 3. So you notice that if we sample with replacement, there are 9 possible samples. Then let's obtain X bar in each case. So for someone whose sample is 1 followed by a 1, then the mean for that sample will be 1.0. Just take 1 plus 1 over 2. Then the second sample, someone who works with the sample 1, 2, with measurements 1, 2, then the sample mean here will be 1.5. Then for someone whose sample is 1 under what? These are comma. Like that, then this will be 2.0. So you notice that the value of X bar is changing from one sample to the other. Okay, then here, this will be 1.5. This will be 2.0. This will be 2.5. And this will be 2.0, 2.5, and finally 3.0. So for someone who uses this sample, then they'll get X bar is 3.0. And someone uses this sample, they'll find X bar is 1.5. So we notice something very interesting here. That is, the value of X bar, changes from one sample to another. The value of X bar changes from one sample to another. So if it is changing from one sample to another, it means that is X bar is a variable. X bar is a variable. Okay, the opposite is not a constant. If you are getting everything here the same value, then we would claim that X bar is a constant. But in this case, we notice that X bar is not a constant. X bar is a variable. Okay, and then this is the logic that we're using here. Just like any other variable, then X bar must be having a probability distribution. We know that variables have probability distributions. Random variables, as you can see, X bar here would be a random variable. So random variables have probability distributions. So even X bar, so thus, winning, I'm coming to you. Thus, just like any other variable, any other random variable, just like any other random variable. Remember, these are random variable because we can assign probabilities. We said that these are random samples. So each of the samples has this probability of being chosen. 1/9. That qualifies it to be a random sample. So just like any other random variable, X bar must be having a probability distribution. Must be having a probability distribution. Then this probability distribution is called the sampling distribution of the mean. Is called the sampling distribution of the mean. So that probability distribution has a special name. It's called the sampling distribution of the mean. That's what we're discussing now, the sampling distribution of the mean. So because we are saying it's a probability distribution, and in the last few classes we have been looking at probability distributions, let's check, because we know a probability distribution can be expressed in form of a table or a graph or a formula. So let's explore using a table, maybe a graph. Then we'll see whether the kind of distribution we are calling the sampling distribution of X bar, whether it's a familiar distribution or maybe it's a new distribution that we need to learn. Okay, so all right, so we're saying we want to find out what kind of distribution, what kind of probability distribution is this that we are calling the sampling distribution of the mean. So let's create a table to represent this information in form of a probability distribution. So the possible values of X bar from this column here, takes the values either 1.0, 1.5, 2.0, 2.5, 3.0. So X is taking those values only. Then from there, we can have a column for probability. So we find out the probability that X bar is equal to 1. You notice that from this column here, it is only appearing once out of 9. So the probability will be this value here, 1 out of 9. The probability that X bar is 1.5, you notice that is appearing either here or here twice. So this will be 2 out of 9. You are just adding these probabilities. The probability that X bar is 2.0, it is this one or this one or even this one. Yeah. So 3 out of 9. Then 2.5 is appearing twice. And finally, 3 is appearing just once. So that is the probability distribution of X bar. I don't know what you can notice. Maybe a graph will be much more appealing. So let's draw a graph. So let's present this thing graphically, or this table graphically. So let's have values of X bar down here. We have 1.0, 1.5, 2.0, 2.5, and 3.0. Then on the vertical axis, we have the probabilities. And here this is X bar. I hope it is visible. So this is X bar. So when X bar is equal to 1, the probability is 1 out of 9. So you can say this is not drawn to scale, 1 out of 9. When X bar is 1.5, this goes up 2 out of 9. When X bar is 2.0, we have 3 over 9. When X bar is 2.5, 2 over 9. And finally, 1 over 9. Okay. Is that distribution familiar? Is that a familiar probability distribution? Or maybe something that is a new distribution? Yes. Is it? Yes.
Distribution.
Sorry?
Normal distribution.
Yeah.
It's normal distribution.
Yeah, clearly this is the normal distribution. If we had so many possible samples, like in the case of fluorescent tubes, would be having so many vertical lines here, then if you fix the smooth curve, maybe it will look like this. It will look like that, which is a normal. How do you know it's normal distribution? Number one, it is symmetrical. It is symmetrical about the mean. You'll notice that this is the mean of the distribution. If you come here, if you come to this table and you find the mean of these values here, maybe you can quickly do that. You find the mean of that column. Yeah, so you have confirmed that the mean of the values of X bar here is equal to 2. And then you have also confirmed that the mean here, which is the mean of the population, is also equal to 2.0. So that means the mean of this statistic here, the mean of the statistic X bar, if I were to denote it like this, mu of X bar is equal to the mu of X, the true population mean, which sometimes we denote like that. Okay, so we notice that the sampling distribution of X bar has a normal distribution with mean equal to the mean of the population, or the mean equal to the population mean, and standard deviation, because the moment you say that it is normal, for the normal distribution to be fully defined, you need to know mu and sigma. You need to know those two things, sigma of variance. So we have known mu is the same as the mean of the population. So if you find the mean of these guys here, you'll get 2.0. What about the standard deviation? I want us to use our calculators to obtain the standard deviation of these two distributions. Okay, so we have already said that the probability distribution of X bar here as a variable is what we call the sampling distribution of the mean. And these are the properties of the sampling distribution of the mean. Okay, so we said that the distribution of X bar is normal. We have seen that. In other words, has a normal distribution. So X bar has a normal distribution with these two properties, with the properties. Number one, so the first property is something that we have seen there, that the mean of X bar is equal to the mean of X, where X is the population information, or the measurements in the population. So That is, the mu of x bar is equal to mu of x, which is just denoted as mu. So the mean of the sample statistic is equal to the mean of the population. That is, mean of the sample statistic is equal to the population mean. And we have done using the example above, using our illustration there, we've seen that for the population, the mean is 2.0, and for the sample, the mean is equal to that. So this is what we are calling mu of x bar. And this is what we are calling just mu, or mu of x. So those two, all the time, those two guys will be equal. The second property, which we may not have shown explicitly, but we can say that the standard deviation of x bar will always be smaller. Will always be smaller than the standard deviation of x. So the standard deviation of the test statistic will always be smaller than the standard deviation of the population measurements. Okay, we have in our example, we have seen that if you compute the standard deviation of the population, remember the population contained these measurements 1, 2, 3, and then the sample, which is x bar, contained those 9 measurements 1.0, 1.5, etc. So we saw that the standard deviation of this variable x bar is 0.5 something. What is important here is not the exact value, but the fact that in all the cases, it will always be smaller than this value. It will always be smaller. It will always be smaller. If we had a larger population and then we sample without replacement, it will be easy for you to see that, because you will notice that the extreme values of x bar compared to the extreme values of x are differing, and you find that the extreme values if you take the difference between the smallest and the largest value in the population, and you compare with the difference between the smallest value in the sample statistic and the largest value, you notice that in the sample statistic we have a smaller range, and range is an indicator of a measure of spread, of the spread of the data. And standard deviation is actually a measure of dispersion or a measure of spread. So using the range, we can show that, or we can illustrate that the sample statistic is less dispersed than the population data. Okay, so we'll not be proving that, but that's a fact. It can be shown. Okay, then the standard deviation of x bar, the standard deviation of x bar is called the standard error. Is called the standard error. Is called the standard error of the mean. Is called the standard error of the mean, and that tells you that every statistic, whether it is the mean or the proportion or any other statistic, has their own sampling distribution and also the standard error. Okay, so usually denoted by SE of the mean, like that, standard error of x bar. Okay, then the standard error of x bar is defined as, so S of E of x bar is defined by sigma, divided by root n, where sigma is the population standard deviation, and n is the size of the sample. N is the size of the sample. Okay, So, so it means that you do not need to use the approach that we used here of calculating the actual standard deviation of the sample statistic, because in most of the cases, populations will be infinite. So it will not be possible or convenient for you to find all the possible values of X bar. So we'll not be doing this. Get the standard deviation of X bar. We'll just be using the value given there, the population standard deviation, divided by square root of n, where n is the standard deviation of, sorry, where n is the size of that sample. Okay. Then in most of the cases, you find that sigma is unknown. When sigma is unknown, we estimate it using the sample counterpart. We estimate the population standard deviation using the sample standard deviation, that is sample standard deviation, which is denoted by S. And we know how to get S. We know that S is always given by the square root of summation of X minus X bar squared divided by n minus 1. So S is always given by that, which sometimes you can rewrite in this format: summation of X squared minus n X bar squared divided by n minus 1, then you take square root. So you can also have it in that format. Okay, so that's what you call, so here there's a new concept that you need to note, that is the standard error of the mean. The standard error of the mean, noted by that, defined by that. Okay, so any question there? So let's move on to the central limit theorem. And the central limit theorem, which we shall be abbreviating as CLT, is at the core of inferential statistics. It forms the basis of the theory that is used in statistical inference. So let's start by that kind of introduction by saying that the CLT forms the basis of the theory used in statistical inference. It forms the basis of the theory that is used in statistical inference. Okay. It states that there are two parts. Number one, if the distribution of X is normal, remember X corresponds to our population information. That means if your population is normal. So if X is normal with mean mu, with mean equal to mu and standard deviation equal to sigma, and samples of size n, and let's say, and random samples of size n are chosen from this distribution, then the distribution of X bar, the distribution of X bar is also normal. Normal with mean equal to mu and standard deviation which here is called standard error, and standard deviation equal to sigma over root n, for whatever size of sample. In other words, for whatever n, for any value of n, whether large or small, then we can assume the distribution, in this case, the sampling distribution of x bar of the mean will also be normal, as you've seen. It will also be normal, irrespective of the sample size, with mean equal to mu and standard error given by that. That is part of what we have seen here, not the story that we have mentioned up there. But there's a rider there that for whatever the size of the sample. For whatever the size of the sample. So this statement in a nutshell says that if you sample from a normally distributed population, population, then the distribution of the test statistic here, in this case, we are calling it X bar, the distribution of that test statistic will be normal, with mean equal to the population mean, and standard deviation, which we are calling the standard error, equal to sigma over root n for any size of n. Okay. Now, the second part of this statement, the central limit theorem, says if the distribution of x is not normal, for instance, if it is binomial or Poisson. So if you are sampling from a binomial distribution, or if you are sampling from a Poisson distribution or any other distribution which is not normal, we say that the distribution of x bar, approaches normal distribution. In other words, we're saying it is approximately, it approaches the normal distribution with mean mu and standard deviation, which we are calling the standard error, equal to, so there's a problem there, and standard, and standard deviation equal to sigma over root n for large samples. Very important part here, for large samples. So as you increase, so let's insert this statement here. As n increases, let's insert it there. So as n increases, that is the size of the sample. So let's insert there. So as n increases, the distribution of x bar approaches the normal distribution with mean equal to mu and standard deviation or standard error equal to sigma over root n. But that's only true when the samples are large. And that's why in research, you are always advised to pick large samples. You're always advised to pick large samples when you want to conduct a research, because there is a possibility either the population from where you are sampling is not normal, or in most of the cases you find that you don't know the distribution of the population. So if you don't know the distribution of the population, then you're advised to always pick large samples. And then using the central limit theorem, you can assume that the test statistic from that sample will be normally distributed with mean equal to the mean of the population and standard error defined appropriately. So that is what we call the central limit theorem. Okay, so for large sample, that is when n is for n bigger than 30. That's what we mean by large samples. So that's the definition of the central limit theorem, a very important concept in statistical inference. Okay, so I want us briefly to look at the application. How do we apply this? Application of the central limit theorem. The application of central limit theorem. And the fact that we've said that the distribution of x bar will be normal. If it will be normal, it means that we can define a standard normal distribution from that distribution. Okay, so let's notice that the central limit theorem, the CLT, means that if we have a large sample, if we have a large sample from a population, the distribution of which we do not know or is not normal, but the distribution is not normal, or maybe you don't know the distribution, we can use the standard normal distribution. We can use the standard normal distribution. We can use the standard normal distribution to calculate the probability, of occurrence of the values of x bar. The probability of occurrence of the values of x bar, since the standardized value, value of x bar is given by, I want you to recall the standardized value of x, we're calling it z, and we're saying that z is given by x minus mu over standard, I want to write in words, standard deviation of x. So in a similar way, we shall be defining the standardized value of x bar, which will be z again. And z here will be given by z. So this is the formula we talk about, will be equal to x bar minus mu, just like the case of x, divided by standard deviation of x bar. Winnie, I'm coming to you. So x bar minus mu divided by the standard deviation of x bar. Here it is standard deviation of x. So that's the difference. So the standard deviation of x bar is what we technically call the standard error of the mean. So this is the same as x bar minus mu divided by sigma over root n. So that's how you obtain the standardized value of x bar. So using the standard normal tables, you can obtain the probability of occurrence of different values of x, or different intervals within which x bar can be found, not x. Okay. So Winnie, what's your question? So but there are cases when when sigma is not known. When sigma is not known, you use z is equal to x bar minus mu over s over root n when n is large. When n is large. Okay. But sometimes you use t statistic. We'll be talking about that later. When sigma is not known, sometimes you can use the t statistic. If the size of the sample is small. If the size of the sample is small and we are sampling from a normal distribution, so those two must be there. If you are sampling from a normal distribution, not from any other distribution now, if you are sampling from a normal distribution and the sample is small and sigma is not known, you use the t distribution. But for now, we shall be assuming that, remember our two assumptions, that n is large. We're assuming that n is large. So sometimes you can use that formula and it will give you the same thing. So this one doesn't matter. Even if the population was not normal, as long as the sample is large, you can always assume the normal distribution of the test statistic there. So let's have some examples. And I want us to do some examples, some things that we mentioned in class the other day when we were introducing ourselves to the normal distribution. Remember we said that 68% of the distribution lies within one standard deviation of the mean. Okay, we said these. We said approximately. 68% will lie between here, like that. So we say this around 68%. 68%. We also said that approximately around 95% of the distribution lies between minus 2.5, lies within 2 standard deviations of the mean. So 2.0 here. So this is 95%. Then we also said that around 99% of the distribution, 99% of the distribution lies within minus 2.5. So, but you notice that these are approximations. These were just approximations. So I want us to calculate the exact number of standard deviations that are found here. Is it 2 actually, or is something else? Because these values here are just rounded off. The same case with 68%. If you are to compute 68%, then the number of standard deviations within which that probability is found below or above the mean, then you'll find that the number is not exactly 1 and minus 1. The same case here. So I want us to do those calculations and notice the exact value of Z, the exact value of Z in all the situations. Now, so let's recall the statement that about or approximately 95% of the normal distribution lies within 2 standard deviations of the mean. So let's recall that statement. Then we are required to calculate the exact number of standard deviations within which 95% of the normal distribution lies, the exact number of standard deviations. Remember, what we are calling here the number of standard deviations is just the value of Z. The value of Z is what we're calling the number of standard deviations. Okay. So solution. So let's sketch the problem that we are trying to solve. So I'll sketch the standard normal distribution where the mean is here. The mean is 0. Then I want to mark here and here. Then this is 95%. So if that is 95%, that's 95%. I want to know this value here, which will be minus, and this value here, Z1, which will be plus. So this is the exact number of standard deviations within which 95% of the normal distribution lies. That's what I want to find out. I want to find the value of Z1. And remember, for the standard normal, I just need to use the tables. I need to use the tables, okay? So because now I'm given this is 95%, I'm given the probabilities here. So I want to get the correct values of probabilities from here. So we can say that we can represent the shaded area here using this probability statement. So this diagram can be represented using probability that we're looking for probability that Z is bigger than minus Z1, but less than plus Z1. And we know that probability is 95%, is 0.95. So that area is 0.95 out of 1, okay? Then we know that the entire area under this curve and below the Z-axis is 1. So the tails, the unshaded part, is 5%. So it means that if you take this plus that, that is the remaining 5% of the distribution. Okay. And because the normal distribution is a symmetrical distribution, we know that this area here, is exactly equal to this area here. It's exactly equal to that area. Okay. So that means I can just say that the area that I've just shaded in green is the same as the upper area times 2. I can say it's the upper area times 2. So I can say that this implies that the probability that Z is bigger than Z1. So that is the upper tail, the upper tail here. The probability that Z is bigger than Z1. If I take that one multiplied by 2, I should get 0.05%. Then dividing both sides by 2, you will notice that the probability that Z is bigger than Z1 is 0.025. Divide both sides by 2. Okay. So I can draw another diagram here to represent this story by saying that we have this 0 is here. This is Z1. So we're saying this is 2.5%, which is 0.025. And if I know that area is 0.025, I know the remaining area from 0 to Z1 is 0.5 minus 0.025, which is 0.475. So this area from 0 all the way to Z1, I'm doing that because our tables are giving us the areas from 0 to Z. Remember what our tables are giving us the area from 0 to some point here. Our tables are giving us that area. So if I know this area here, if I know this area, which is 0.475, then it is possible for me to find the value of Z. And that will answer the question here. The number of standard deviations above or below. Because I'll use symmetry to locate the value of Z2, because I just negate the value of Z1. So let's go to our tables, the standard normal tables, and look for the Z value that will give us the area of 0.475 above 0. So here are the standard normal tables that we shall be using. We are looking for a value of Z, which will give us an area of 0.475 from 0 all the way to, on the positive side. So checking through the values of probabilities given here, you notice that that value is exactly here, 0.4750. So that corresponds to a Z value of 1.96. 1.96. So that is the exact number of standard deviations above the mean. So thus, we are talking about this area here. So this is 1.96, and this one is minus 1.96. So this is what will give us 95%. This is what will give us 95%. So when we say that about 95% lies within 2 standard deviations, this is the number we're referring to. This is the number that we are rounding off to 2. We are saying is around 2, around 2.0 standard deviations above, within the mean, where the mean is this guy always. This being the standard normal distribution. So that's how you can compute the exact number of standard deviations for any given percentage. And I want you, we can just quickly do that. We can quickly try the case when we're using 99%. Let's work with 99%. We said around 99% of the distribution lies within about 2.5 standard deviations within the mean. So we're talking about this area here. This is 0, and we're talking about some Z here and some Z2 here, some Z1 here, which is minus. Then we're saying this is 95%, 99%. So we need to look for this value of Z. We need to calculate that value of Z. So we can say that twice the probability that Z is bigger than Z1 is equal to the remaining percentage, which is 1%, which is 0.01. Okay. And then we can say that probability that Z is bigger than that, Z is bigger than Z1 is equal to 0.00, 0.005. Okay. And then we're using our diagram here. We have 0, then here we have Z1. If this is 0.005, we know the remaining area is, so the remaining area here is 0.495. So that's the area we should look for in the tables. It will give us a value of Z, 0.495. 0.495. So from the tables, we notice that the nearest value is given by these two. We have 0.4949 or 0.4951. And you can speculate that the actual value we are looking for is in between 2.57 and 2.58. So maybe 2.575. But for convenience, we use the upper value. We use the upper value. So 2.58 is the exact number of standard deviations. So this is 2.58. So that means 99% of the normal distribution lies within these. So you can say 0. So here we have 2.58 and here minus 2.58. So this is where you find 99% of the distribution. So the value here, 2.58, is what we were saying in our earlier statement, that is about 2.5 standard deviations within the mean. As you can see, the actual value number, or the actual number of standard deviations is slightly higher than 2.5. So you can repeat the claim for the example that or for the statement about 68% lies within plus and minus 1 standard deviations within the mean. So you can try that. You can try that after class. Then that way you should be able to calculate any other probability. So you can use the statistic that you've defined here, the standardized value of X bar, to compute different probabilities of X bar. And we'll be finding much of that in our first quiz. So we need to practice more on that. Okay. So I want that to be the end of today's class. Any questions?